All right, today I'm going to be giving a basic demonstration of encryption. Now, encryption is quite complicated and uses some special algorithms to prevent it from being reversed, but this is a pretty good low-level example using matrices, matrix multiplication. So we're going to start out with a 3x3 matrix containing this message. This is encoded in ASCII. So 72 equals capital H. 105 is E. No, 105 is I. Sorry about that. 32 is just space. 67 is a capital C. Then 108 is an L, lowercase. Of course, the rest is lowercase. 97 is A. And 115 is S. Also 33 is exclamation point. So 108, 97, 115, 115, and then 33. So this says H, capital H, lowercase I, space, capital C, lowercase L, A, S, S, exclamation point. Hi, class. So then we're going to call this matrix A. Run a little tight on space here. I need a lot of space. You'll see in a moment. So then we're going to say our key is matrix B here. And matrix B is also a 3x3 matrix containing some random numbers. So 4, 4, 8, 1, 3, 1, 9, 2, 1. Okay. So this is somewhat random. I just asked people for some numbers and got these. So the idea is if we take our message and multiply it by this matrix, we get our encrypted message, or what we're going to call matrix C. Going to do the magic star thing here. So, for those who haven't done matrix multiplication before, this gets a little messy. So we basically take these three numbers right here, this first column, and we rotate it 90 degrees, and we multiply the 4 by 72, the 1 by 105, and the 9 by 32 to get what is our first number of the final grid. So if we're going to draw this, we're just going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is just placements of our numbers. So to get the slot number 1 in this matrix, I know this is probably incorrect notation, but the first slot equals 4 times 72 plus 1 times 105 plus 9 times 32. Equals 681. Now, to save some time, I'm going to write all this out for you so you can see this just fine. And for readability, I'm just going to go down the rows because we jump down. So this 419 is multiplied this, and this. So matrix slot 1 here is 472, 1, 105, 9, 32. And then matrix slot 4 is 4 times 67 plus 1 times 108 plus 9 times 97, and then moves down 1. And then as you move over here, multiplying this by the first row gives you slot 2, second, 5, third, 8, so on. So now that we've done all of this painful math, we can write our final actual C matrix. So matrix C is, need a little space for this, 681, 1249, 872, 667, 786, 871, 713, 741, and 1068. Gonna hope this is correct or it won't work properly. So this is matrix C. If you look in the data table, the highest numbers in here are not in the same slots as the highest numbers in here. So without this key, you can't really undo this without guessing. And even then, in order to get your original message, you need to multiply this by the inverse of the key. This only works with square matrices because otherwise you get a different dimension on the way out and then you can't multiply by the inverse. So because inverse is quite ugly, I can tell you what the inverse is here. So here is the inverse of this matrix. It is quite annoying to multiply these two back because then we get these ugly fractions. But knowing that this works correctly, I know that this is the original message, and I'll show you on calculator. So in matrices, I have a 1 by 1 that has nothing in it, 3 by 3 matrix B that has the key right here, and in matrix C we have this encrypted message. So if I take the inverse of matrix B, which is this ugly thing, we can convert this into fractions. You can see this is the same thing that I wrote down here. And we're going to store this in matrix A. So then, if we take matrix C, our encrypted message, and multiply it by matrix A, we get our original message, fully intact.